Hello, my name is Sarah Jane Potts and I'm a research engineer working at Specific Information Knowledge Centre at Swansea University. I mainly specialise in printed electronics such as printed PV, so photovoltaics, as well as resistive heaters, which will be covered in today's talk, looking at different engineering solutions which can be used for off-grid homes. So why do we need engineering solutions to go off-grid? Well, the reason being is we kind of have a climate emergency and we really want this planet to last longer. And in order to do that, we need to reduce our greenhouse gas emissions by at least 80% before 2050. At the moment, here in 2020, we have around about 30% of electricity produced by renewables, which is what we were on target for. However, it does depend on the weather. So is it windy enough? Is it sunny enough? And all of these things come with their demands. Therefore, we need to come up with more solutions, especially as we want to be able to decarbonise by 2030. But this is made even harder by the fact that we have an increase in transport requirements with a far larger number of electric vehicles now coming out, and also the electrification of heating. So our demand's going up, which means we need to create even more sustainable energy solutions. But how do we do that? So I work for a group known as Specific at Swansea University who specialise in looking how to create buildings as power stations. So my research group looks at creating self-sufficient, sustainable energy-based buildings and works mainly on perovskite-based solar cells, thermochemical storage, printed heaters and batteries, all of which will be covered in today's talk. So what we have on screen here are two demonstrations that we have at my university at Bay Campus at Swansea University. The first one that was created back in around 2016 is the active classroom. So this is a completely off-grid building. Well, it's put back on grid, but only to give electricity to the grid, not to take it, as we sometimes have so much excess that we don't know what to do with it. We've already got batteries to store it, so we've got batteries at the back. We've got our solar panels integrated and printed onto steel panels, and those are making up our roof. And then we also have a variety of other demos looking at semi-transparent solar cells as well, which are on some of the windows, and transpired solar collectors, which I'll go through later, which look to take in the hot air from outside and use it to heat the building, as well as many other things like resistive heated panels, the really nice toasty underfloor heaters, which can be programmed easily. And then more recently, we also have the active office, which uses very much similar technology, but also shows that if you want to have a nice fancy curved roof with PV on it, you can do that too. And is a fully functioning office, which is also off-grid, and both buildings are used to charge our fleet of electric vehicles, which means it is very much put to use. However, we haven't just created some demonstrations in our campus, we have also assisted with the production of the new active homes, with NEEF active homes, which are completely off-grid with solar PV roofs, just like the ones used in the active office and active classroom, as well as transpired solar collectors, which will take in the hot air and be used for heating. And in order to still provide energy when the sun isn't shining, which sadly in Wales it very rarely is, although it has been whilst we've been in isolation typically, we have a battery in the shed, which means that you can still be able to turn on your heating and whatever you need, more importantly in this one, your TV, because your heating is provided in another manner, even when the sun's not shining, which is great. And then we can also use that in other applications. So something we're currently working on are solar powered active train shelters. So on these shelters, you will have curved solar panel roofs, you will have batteries hidden away so that as with the homes, you can have energy even when the sun's not shining, and that will power a variety of interactive panels, so you know what time your train's coming, a load of adverts, and even the ability to charge things like your mobile phone. So those will be really great when they come through soon. So today I'm going to give you an overview of a variety of things that we are currently working on, going from resistive heaters to transpired solar collectors, a bit on thermochemical energy storage, batteries, which are needed to store the energy, but most importantly, how the energy is produced. So I will go through a few forms of renewable energy sources. So as I mentioned earlier, with an increased use of electricity in forms of cars and forms of heating, we need to produce more sources of renewable energy. And we have a variety of options, thank goodness, so that we don't just depend on one. And if you have a look at the data right here, this was done on May the 4th when this presentation was created. And at that point in time, we had around 17% of our UK energy being produced by solar, about 8% by wind, and a little less than 1% from hydro. So you also need to bear in mind that this will be weather dependent, as that was a really nice sunny day, but not a very windy day. So sometimes those values could be completely reversed. And also we have got some hydroelectric power stations which only produce energy when it is required, as with nuclear, so it can be used as a topper. But altogether, that's allowing us to create a far larger percentage of renewables than we used to have, but we want that to be everything very soon. So let's go through some of those options. So the first one, which I will cover more on later, is solar in terms of photovoltaics and thermal storage, but we'll be looking more at the photovoltaic side, although if you have any questions, you are more than welcome to ask on either of these. So with solar, you have a humongous range of designs available, which I will cover later. And as I showed you earlier, these can be integrated into the roof, so they don't just have to be retrofitted, which is fantastic. However, in order to increase your efficiency and make them worthwhile, it does depend on what direction they're orientated to, as south-facing solar cells will get a lot more of the sun rays than any other direction, making them substantially more efficient. So when it comes to future-proofing houses, we will obviously have to make sure that they're orientated in the right direction. The second one is wind. So you will see a load of wind turbines out and around now. I've even got one that I can see right out of my window here, which you'll have a photograph of right there. So this is what I'm seeing. So this is quite a large wind turbine. This isn't something you would strap to the side of your house. Typically, if you want to have it for an off-grid home, you would have around 400 watts to 20 kilowatts. And this can either be mounted onto a pole, as with the one outside my window, or it can be mounted onto the building. However, to make this worthwhile, you will need to have windy conditions. So if your house is in a nice little sheltered area, it's probably not the technique for you. A third option, which you could have at your home, would be hydro. So for this, you've got a few more complexities. You will first of all need permission from the environmental agency and neighbouring landowners before you even consider drawing up designs for one of these. You will definitely require a stream or river for your water source, a flowing water source, so you can't just shove it in a pond. And it also depends on the location. So what direction is the water flowing in? How high is your riverbed? And are there any environmental restrictions? Are there any forms of wildlife around there which would not benefit from having hydroelectric wheel or turbine put in? But a really nice example, a local example I have, is from Aberdalis Hydroelectric water wheel. And this is at the Aberdalis National Trust location at the old tin works. And in this case, this is a renovated water wheel done in Port Albert, which enables them, when they have it attached to a generator, to produce enough electricity to power their displays inside, which was really cool and could really suit a nice little cottagey home, which I would love to do sometime in the future. But how exactly do these things work? So let's start with the kinetic forms of energy, movement, so the wind turbine and the water wheels. So in the case of the water wheel, when the water goes down, it will spin the wheel round and round in the same way that the wind will spin the blades of the turbine round and round. At that point, it is sent from a shaft to a gearbox, which will amplify the speed that it is rotating at, which is particularly useful if you are in an area where it's not going particularly fast. And this will then go to a high-speed shaft, which will drive the generator. Or in the case of some larger and more industrial wind turbines, specifically ones that you will find out at sea, these will not require a gearbox and instead has a very large generator, which allows it to be directly driven. And all of this enables the kinetic energy to be converted to electrical energy by electromagnetic induction. So how does electromagnetic induction work? So at a very basic level, so this isn't what it would look like inside a wind turbine. It will be substantially more complex than that, but we'll go through the basics today. So typically in a wind turbine, you would have the first diagram. So you would have a series of coils, so usually copper coil, inside a spinning magnet. And as the magnet goes round and round and round, this will induce a voltage producing a current. Or the alternative is that the coil will be inside, strapped to your shaft, and that will go round and round and round inside a magnetic field, both of which enable the voltage to be induced, producing an induced current. But what does this look like? So as your magnet turns by 180, so we'll look at this example, the one side of the coil will align with the magnetic field, and this will enable a potential difference to be induced in one direction. And then as it turns to the opposite side of the coil will then align with the magnetic field, and a potential difference will be produced in the opposite direction. And in this case, this is producing a sine wave in the form of an AC generator. So this is how we produce our energy. If you want to make a basic example, all you need is some copper coil and a magnet. If you spin it round and round and you connect it up, hopefully you'll be able to light up something like a little LED if you want to try this out at home. But moving on, so the one I'm a little bit more interested in, is more connected to what I do, is how do we get electrical energy from solar energy? And this is in the form of the photovoltaic effect. So in this case, photons are excited between two electronic bands, which are the valence band and the conduction band. So if these bands were too close together and touching, then you would just have a conductor. If they were too far apart, you would never be able to get the photon to jump, so this wouldn't be conductive. But if you have it somewhere in between, you're in the realms of a semiconductor, and this is where it starts to get useful for us. So when photons are excited from one to the other, this will create a voltage difference between the two electrodes. But let's try and take this and apply it to how our PV works. So in a very simple PV device, as you have illustrated here, you will have two materials of different electronic properties. So here is your one contact and here's the other. One will be electron rich and one will be electron deficient, producing your working and your counter electrodes. These will be placed between two electrodes. So you will then have your conduction bands, your valence and conduction bands from earlier, between two contacts, forming your working and counter electrodes. And then as light strikes the electrically different materials, this will form pairs of electrons and holes. And as separated at the interface between the two materials by an electric field, and this will result in generating electric power. So, as I mentioned earlier, there are lots of different forms of solar cells. So you can see a collection here and how they rate in different cell efficiencies. So the more common ones are your purple ones, but these are typically a little bit more expensive and usually silicon based, which means they're not really available for all of us. Instead, what my group are looking at are more cost-effective methods which don't require silicon or rare earth materials, and these are in the form of photovoltaics, which you can see by this little line here of the orange circles with the yellow centers. And you can see quite a dramatic and rapid improvement in the efficiencies over time. So hopefully that will continue to spike its way up. So this is the most recent graph by the NREL going up to 2020. And if you want to be able to see a bit more on this, you can just go to their website, which is put here. So the cell that I work on, Perovskite solar cells, are typically screen printed, which is what I specialize in. And it is created in a series of layers. So this goes from so to go through each layer, you have FTO coated glass, and then you have a spray coated layer of titanium dioxide, followed by a mesoporous stack of screen printed titanium dioxide, on top of which you will then get screen printed zirconia. And then to top it all off, you'll have my favorite, some screen printed carbon. And when you have this in the desired pattern with the correct spacing, this is how we are going to be able to have a photovoltaic effect in order to transfer our solar into electrical energy. And this example you see directly below is one of our most recent designs. So this is an A4 size cell, so it's currently relatively small, but hopefully with a little bit of help from here, we'll be getting a lot larger soon. And the advantage of things like this is because they are printed, they can be printed onto just about anything, whether it's glass, metals, or plastics, which gives it the potential to be semi-transparent if you change some of the materials, and also be printed directly onto the roof materials, so you don't have to retrofit anything on. However, solar is only useful, as are all of those things, only useful if you can store the energy, so you can use it when it's not windy, when the stream isn't flowing because the water levels are too low, or when the sun isn't shining. So to do that, we need batteries. So let's go a little bit into how batteries work. So the fundamentals of it is that energy is stored in the battery, so you can use it whenever it's required. To have this happen, you need a pair of electrodes, one which will be the anode, one will be the cathode, and when it is discharging to give out the energy, you will have the electrons flowing from the anode, which will be oxidized in the same way that if you leave a car out for too long, it will start to rust. So this is oxidizing. And then your electrons will transfer the way through the electrolyte and accepted by the other electrode, which is the cathode, which will be reduced as it gains these negative electrons. And then if it was a rechargeable battery, like some lithium-ion batteries and many of the other ones we require to use when it comes to solar, you will then be able to reverse this process. So whichever one's the anode becomes a cathode and vice versa, and then the electrons will flow the opposite direction, still going from the anode to cathode, as you are still oxidizing the anode, which in this case is the other material, and then reducing the cathode, ready for it to flow right back out when you need the energy. So this is only possible when you have two metals which are dissimilar in the case of most batteries, as is simply a form of electrochemical corrosion known as bimetallic corrosion, where you have two metals with very different potentials which are in electric contact whilst immersed in an electrically conducting corrosive liquid. And these different potentials of metals in liquid will allow that current to flow from the anode to the cathode, corroding the anode. So here are a few different electrode potential values, which are in reference to a standard hydrogen electrode. So in the case of a basic voltaic pile, which is also used to produce things like penny batteries, you will have a series of, say, copper coins and zinc washers, and because they have a potential difference of 1, this will allow the copper to oxide as the zinc is reduced, thus enabling it to act as a battery. So in the case of a basic little penny battery, you can then light up something like an LED to show that it is definitely producing energy. So when it comes to batteries in our current buildings, we have a variety, but the majority are big lithium-ion batteries. So a bit like the batteries that you would find in your mobile phone. These are rechargeable, which is fantastic because it's what you need. So the sun can charge it up and then it can let the energy out whenever it's required. So these are being used in the active homes in the form of some of the Tesla Powerballs, and also have some BYD lithium-ion 110 kilowatt-hour batteries being used in our active office. And then on the other hand, we have some zinc bromine flow batteries, which are being used in our active classroom at the moment. So at the moment, we're just trying out what's good to have a better idea of how good they will be in the long term. But battery technology is always advancing, so we're always waiting for the next best thing. However, as well as producing electrical energy, we can also produce heat. So something else we have strapped to the side of both our active office, our active classroom, and the active homes are transpired solar collectors. So these work as an active solar air heater in the form of a sheet of coated micro perforated steel. So to put it simply, it's holy steel. You just have lots of holes in a sheet of steel which is coated with a particular coating to absorb lots of heat. So these are usually installed on southerly facing walls for the same reason that you need those solar panels, as this is where most of the sun rays are going to go to enable it to heat up. And in the same way as if you were to lean on a car on a very hot summer's day, you would find it rather painful and scorching. These walls will also enable the heat to be absorbed, but instead of it just heating up and causing you to get burn marks, it will actually draw the heat through the little holes, which will then be sucked through into a fan, which will then transport it throughout the house. So normally these coatings need to be a colour which is going to absorb a lot of heat, so black is typically the best colour for this. However, black isn't always fashionable, so that it has been found that lime green is also very good at absorbing heat, so most of the walls are typically lime green and enable us to take in the hot air and then use it to heat our house up. However, we don't always want to use it immediately, in the same way we don't always want to use some of our solar heated or our solar photovoltaic energy. So what can we do with that excess of energy if you don't just want to put it in a battery? That's when these come in. So an alternative heating method is thermochemical storage in the form of a salt in matrix material. So this forms a form of interseasonal heat storage, so you can store it when you don't want it and also transport it from place to place. So the way this works is thermal energy in the form of heat can be stored by passing hot air over this salt in matrix, which in the case of what we're looking at the moment is made up of calcium chloride and vermiculite. And this will create a chemical reaction that locks the energy into the material, and then the heat can be released when you need it by an exothermic reaction by passing humid air over the salt in matrix. So this is a fantastic way of storing our heat, which is currently being investigated by the group with some really great researchers. But moving on to the favourite part, in my case is something which I particularly enjoy working on, are resistive heaters. So these are screen printed underfloor heaters which produce a uniform heat using very low temperature, large area panels. These work particularly well with low voltage renewable energy systems like solar and can be printed onto a range of surfaces, in this case including coated steels, which when you put down a layer of carbon ink and pass a current through it, will enable it to heat up through resistance, and then according to the voltage you put through, you can change temperature as well. So it's really nice and easy to manage and very easy to install when compared with some of the current alternatives. As you can see there, you can just lay them down as panels however you need. But today I'm not going to be showing you huge panels. I'm going to be showing you some which I have to hand and also which you can make at home. So cork is a very firmly stable material to a temperature you probably won't be able to guess, around 200 degrees C. But you realise, fantastic. Which means that if I then take a bunch of carbon ink and I screen print it onto a cork coaster, and I then have some silver tracks also screen printed on as my buzz bars, and I connect that up to a pair of 9-volt batteries, which you can see inside there, I am then able to produce a nice toasty warm coaster which I can use to heat up my drinks or warm up my hands when I'm cold in the office. So to prove that this is in fact conductive and not just something I scribbled on, I will get my multimeter here, lie it on the side, and if I turn it on to resistance measurement so you can see how resistive it is, so opposite to conductive, I can then show you that it is definitely producing a value around, I think, 100, 120 odd ohms. So it's not particularly conductive, but we don't need it massively conductive, as we want it to be resistive enough to generate some heat. So as well as the design we have here, you can also produce it in a variety of designs. So this is actually one I painted. So if anyone wants to grab some conductive ink like the one in my hand and grab a paintbrush and paint some of this on at home, if you connect it up with some batteries, you will actually be able to generate a nice little bit of heat. But today I'll be showing you the one which was screen printed, as it's a little bit more conductive, which means it's stable enough that it's going to produce a nice bit of heat. So I'm going to show you that today using my FLIR 1 infrared camera, which I can strap onto my phone. If I get it switched on, you can just see how it attaches here. Just takes a little while to warm up. You can see it's quite a nice simple device that just straps onto the side. So you may have seen in the local news that people are currently using infrared systems to strap onto helmets to check who has COVID-19. It's not much more complex than what I have in my hand here. So if I turn this around and get this in place, you can just about see, if I align it with my little cold fingers, where our coaster is. There we go. There's our coaster. But now if I switch it on, you should be able to see it heat up. So instantly, if I put my fingers there just to prove this is real time, you can see it is definitely heating up to something which would be really nice if you have cold hands, just to get them a little bit warmer. And this can be used in a similar way in our underfloor heaters. And because we can produce them in a variety of designs, so it doesn't just have to be like that, you can have ones like this. You can even have ones like this, but as it's a long thin track, it's quite hard to get conductive. Or you can have nice big solid areas. All of these have the potential, when they are connected up, to heat a nice uniform area, which can be used in a variety of situations, including clothing, automotive devices, and also on the back of your chairs, but they are really, really good as underfloor heaters. So I hope you've enjoyed this session. And if I just give you a quick summary. So renewable energy sources can be used to generate energy from the home, and batteries can then be used to store this energy, while solar heater systems can be used to generate heat. And if you have too much, thermochemical heat storage systems can be used to store that, while things like programmable low voltage resistive heaters can be used for your underfloor heaters, which means that there are a variety of options to choose from when creating your off-grid home. So it can be made useful for just about anyone. So I hope you've enjoyed this session. And I would also like to thank these guys. And if you have any questions, just let me know. Thank you.